Hello everyone, welcome. And in today's lecture, we will discuss statistically independent events. Now, we have done a lot of discussion on what is conditional probability and Bayes theorem, which is also a theorem related to finding some kind of conditional probability. So now we are in a position to discuss what are statistically independent events. Suppose, now I don't want to go to the formula directly, and hence I would like to start with an example. Now, suppose I tell you that I am tossing a coin and then I am rolling a die after that. So I have a coin, I'm first tossing that, and then after that I am rolling a die. Okay, one after the other. Now, if I get a head in the coin, what is the probability that I get a 6 when I roll the die? So I'm asking it in terms of a conditional probability that okay, I tossed a coin and I got a head, and now I'm rolling a die. What is the probability that I will get a 6? Now leave all the formulas behind. Don't think about any formula. Just have using your common sense. What do you think will probability of rolling a die be? You thought it right. It won't change, right? What I get in the coin, now suppose I say that I got a tail on in the coin, will that affect my die roll? Not at all, because that is not related to me tossing the coin. There is no relationship there. So if I ask, if I ask it in a mathematical way, you can see that if I say that what is the probability I get a 6 when I roll a die, given I get a head from a coin toss, by the definition of probability A given B, it is probability A intersection B by probability B. Okay, so the probability will be I get a 6 with die and a head from the toss given divided by probability head from a toss. And above, what is the probability I get head from a toss? It is half. And what is the probability I get 6 with the die? It is 1 by 6 divided by probability head from a toss is half. And that gets divided. So my answer is 1 by 6, which is actually probability of 6 when I roll a die. All right. So think of independent event in a way that occurrence of any particular event B has no effect on the probability of A. So if I write this in a more standardized way, probability that A happens given B has happened is probability A. It doesn't matter that B has happened, the probability of A remains constant. And another way of writing this, which is actually the most famous way of defining independence of events, is so we know by definition, right? And by the independence definition, I know that this is A. So this means probability A intersection B is probability A into probability B. So basically, what is the probability that A and B happens? It is just independent probability of A happening into independent probability of B happening. That's what independence helps us, and that's what independence that's how independence simplifies things. For example, if independence was not the case, then if the two events were not independent, then my probability of A intersection B will be this, right? Or this, whatever. And in that case, I have to find this particular probability, and that may become very difficult to calculate in many cases. Hence, this independence condition simplifies the intersection probability to a large extent. And although I was explaining this to you before I gave this formula, over here I have done the exact same thing. The probability of 6 with a die and probability of head from a toss. I have just multiplied probability of 6 with die into probability head from toss. So I actually used the formula before giving you the formula, but that you get the intuition right. So, an idea of one event happening having no influence on another is called statistical independence. That is the idea of statistical independence. It doesn't matter what event happened, the other event happening doesn't really care. Okay? Now, I'm going to give you some examples which will make this concept even stronger for you. And there are three examples in front of you, and I'm going to give you a second, and you're going to think if they are independent or they're not independent. Okay, now first one, we actually discussed that you toss a coin and then roll a die. Are these statistically independent events? Yes. Now suppose I pick a random person in a mall and I just ask, are you left-handed? Suppose he says, yes, I am left-handed, and the other event is that today is a Tuesday. Now that again is independent. Now suppose I ask you, what is the probability that it rained today, given that I see wet roads? Or what is the probability there are wet roads, given that it rained today? In whatever way I ask. Now that can have some sort of dependence, right? Because when it rains, it is more likely you get a wet road. You have a wet road. So these are dependent events. These are not statistically independent events. I would like to end this concept majorly by giving you a thought process whenever you think of independent events, and that is when events don't affect each other. It is called statistical independence, and the chance of both happening is simply the chance of one multiplied by the chance of another. The complications of finding the intersection of two events of both happening together is completely simplified, because we are now looking at the independent events probability and just multiplying them. Okay. So that is the concept of statistical independence of two events. When you come to three events, the formula has to be defined in a very concrete and distinct way, because not three actually, any event more than two, and we'll come to that. That's out of scope of this lecture. But one thing I want to say before I leave you is define and distinguish between mutually exclusive and independent events. Although they are very different concepts, but people get very confused, maybe because the terminology and maybe the English meanings may mean the same. But these are two different concepts, and I want to bring that distinction here. So, two events are mutually exclusive when they can never happen together. They cannot, it is impossible for them to happen together. For example, if I roll a die and I say, what is the probability I get a 2 and I get a 5? That's 0, right? I can't get a 2 and a 5 together. I will either get a 2 or I will get a 5. Whereas, so for mutual exclusivity, if I'm talking about two mutually exclusive event A intersection B, that is always 0 for mutually exclusive. And independence, think of this carefully, they can happen together. There is no guarantee that they won't happen together. But one doesn't influence the other in any way. If one happens, the other will happen with the same probability. All right, you're not getting any new information about the second event. So they are unrelated together. It's not that they're impossible together, because how can it be impossible together? We have ourselves given the definition that probability A intersection B is probability A into probability B, right? I'm not saying that it's 0. So that is for mutually exclusive. So they are unrelated, but they are not impossible. They are free to happen together. For example, if I toss a coin, what is the probability that I get head in the first and in second toss? So in that case, it would be 1 by 2 into 1 by 2. So yeah, by this I would like to conclude this lecture. I hope you understood the differences between mutually exclusive and independent events. Thank you. I'll see you again.